In this video, we discussed thermal expansion. Most materials expand when their temperature increases, and we have already mentioned that this happens for liquid ethanol, for example, in a thermometer. As the temperature increases, the volume of liquid increases. And most solids also expand, and we can measure this expansion. For example, in this demo, I have a long brass rod. One side of the rod is resting on a needle, so that if the bar expands, the needle will rotate. So I take a torch to increase the temperature of the rod. It takes time for the temperature to increase, so I move the torch to warm up the whole rod. And as the rod warms up, you see that the rod becomes longer and the needle is moving. Now let's discuss this situation. So let's say that you have a rod at a temperature T0 and the rod has a length L0. Now if you increase the temperature by an amount delta T, then the length of the rod increased by an amount delta L. And delta L is given by alpha times L0 times delta T. Now in this relation, alpha is the coefficient of linear expansion in inverse Kelvin or in inverse Celsius. Right? Remember that because Kelvin and Celsius have the same size degree, the value for temperature difference delta T is the same in both units, right? Because it's a delta. Alpha will be a number that depends on the material. So let's analyze this relation in detail. You see that the change of length delta L is directly proportional to the change of temperature delta T. Right? So if you double delta T, then you will double delta L. Also, you see that delta L is directly proportional to the initial length L0. So if you double the initial length L0, then you double the change of length delta L. Then you see that the coefficient alpha will depend on the material. So we'll have materials with larger coefficients. For example, aluminum has a coefficient of 2.4 10 to the minus 5 inverse Kelvin. And quartz has a coefficient, a much smaller coefficient of 0.04 times 10 to the minus 5 inverse Kelvin. So you see that those are really small numbers, right? Alpha is of the order of 10 to the minus 5 Kelvin minus 1. So for a delta T of 100 degree, the relative change of length, delta L over L, will be of the order of 1,000. So that's a very small effect. Now, how do we understand thermal expansion? Right? One model that helps to understand this is to consider the interactions between the atoms in a solid. And you can model those interactions as little springs between the atoms. This model is somewhat correct in the sense that if you try to elongate a solid, the interactions will resist this. And if you try to compress a solid, the interactions between atoms will also resist the compression. So near some kind of equilibrium distance between atoms, the potential energy resembles the potential of an harmonic oscillator. But the key, in fact, to understand thermal expansion is to realize that this is not exactly correct. And the potential is not exactly like a parabolic potential. You can see at short atomic separation, the potential energy is increasing much faster compared to how it increased at high atomic separation. Right? So with respect to the spring model, you can think of this as due to the fact that it is easier to stretch than to compress a spring. And because of this asymmetry, when you raise the temperature, you raise the energy, and the atoms will oscillate with a larger and larger amplitude of displacement, but the average will shift towards higher and higher separation. If the potential was symmetric, the average would always be the same. But because it is easier to stretch than to compress, at higher energy, the average is shifted towards higher atomic separations. And so that's why the material expands. Now, here is a question for you. Let's say that a solid object has a hole in it. Then what happens to the size of the hole when the temperature of the object increases? Well, first you might be tempted to say that the hole will shrink, but that's not actually what happens. Right? In fact, the size of the hole increases too. And to understand this, think of the plate without the hole in it. Right? As you increase the temperature, the size of the plate increases. So the material that is at the place of the hole also increases, so the size of the hole increases. Now, there is a cool demo that we can do with this. First, let me mention that if the size of the hole increases when we increase the temperature, then it will shrink when the temperature decreases. So here I have a brass ring and a ball that can just fit through the ring. Now, if I cool down the ring, then there will be a thermal contraction of the ring and the hole will become smaller. Right, so here I use liquid nitrogen to cool down quickly. And I think that it is cold now. And now you see that the ball does not fit into the ring. So the hole becomes smaller when decreasing the temperature. Now, in fact, if I want the ball to fit through the ring again, I need the ring to warm up, or I can try to cool down both the ball and the ring. Right? So let's try to do that. I'm now cooling both of them so that the ball will also contract. And now the ball takes longer to cool down. Let's see. Okay, so it looks like it's cold enough now. Oh, actually, no, it's not cold enough. It doesn't fit. So let's cool it again. All right, now both are cold, and so they are both contracted, and you see that the ball fits in the ring. Now, similar to the coefficient of linear expansion, which describes the expansion of a rod with a length L0, there is also a coefficient of volume expansion. In this case, the relation is delta V equal beta V0 delta T. And beta, in this case, in this formula, beta is the coefficient of volume expansion, also expressed in inverse Kelvin or inverse Celsius. And in these tables, you can see a couple values for the coefficient beta. So look at brass, for example. The coefficient of linear expansion alpha is 2 × 10⁻⁵ Kelvin minus 1. And the coefficient of volume expansion is 6 × 10⁻⁵ Kelvin minus 1. So it is 3 times more. And in fact, you can check other values in this table. The coefficient beta is equal to 3 times the coefficient alpha for isotropic materials. And those materials in the table, most of them are isotropic, so this applies. Now, in this table, if you compare the values for metals to the values for glass, you see that the coefficient of volume expansion is larger for metals than it is for glass. And so if you increase the temperature, metals will expand more than glass. And if you decrease temperature, then metals will contract more than glass. And you probably know this trick. When you can't remove the lid from a jar, you can warm up the jar lid with some hot water. And since the lid is metallic, it will expand more than the jar, which is often a glass jar. And so then it becomes easier to open. Now, most liquids also expand when warming up, right? And they contract when cooling down. And this is true for water also, but except when water freezes, right? You probably already know that when water freezes, it expands and becomes less dense, right? And this is why ice floats, for example. But this is quite an exception for water, right? Most materials also contract when they freeze, but water is special. And another special property for water is that, in fact, this exception starts before freezing. What you can see on the graph is the volume of water as a function of temperature. In the top graph, you see that the volume increases when you increase temperature, right? Completely normal. But on the bottom graph, you see a zoom in the region near 0 degrees Celsius. Right? And you can see that between 0 and 4 degrees, the volume decreases with temperature. This is a tiny effect. We really need to zoom on the graph to see it, but it has some important consequences. In winter, the air gets colder and cools down the water. And as the water cools down, it contracts as most materials do. So it becomes more dense and it goes to the bottom of the lake. So the warmer water stays on top and gets cooled by the cold air again. And this continues until the temperature of the lake reaches 4 degrees. So eventually, when the temperature of the water reaches 4 degrees Celsius, at this point, when it cools down below 4 degrees, it will expand. And so it will not become more dense, it will actually become less dense, and it will stay on top. And so if it stays on top, it will continue to cool down, and eventually it will freeze. And because ice floats, it will stay on the top. And ice is also a good thermal insulator, so it will prevent the bottom from cooling much faster. And so the bottom of the lake remains at 4 degrees and will not freeze unless the entire lake becomes frozen. Right? And because of this, then the fish can stay in the water, which is at 4 degrees during the winter. And you see that if water was like most materials, then the lake would freeze easily. Right? It would actually freeze from the bottom, and then the fish would eventually be pushed towards the top, and they would die. And so most animals and plants would not be able to survive winter, and life would not develop, and maybe humans would not even exist, and I would not be here telling you all about this. Now, if you continue your studies in physics or chemistry, you will learn that this exceptional behavior of water is related to the property of what we call the hydrogen bond.